Told you that the key to a galactic scale technological civilization isn't actually found in advanced silicon chips.
Right, yeah. Or, quantum superconductors running at absolute zero.
Exactly. And it's definitely not in those massive world-spanning steel megastructures we always see in sci-fi. I mean, think about the way we build that ore down.
Yeah, just to force it into these rigid, static shapes.
Right. It's an incredibly violent, high energy,
Mm.
and let's be real, ultimately inefficient way to create infrastructure.
Yeah.
But what if the blueprint for our ultimate technological future is entirely different?
Totally different. Like, fundamentally opposed to that.
Yeah, what if it is actually hiding inside misfolded proteins, like the exact same class of biological structures originally famous for causing neurodegenerative diseases?
It's a wild premise. It completely inverts how we traditionally think about material science or, biology and the whole future of human infrastructure.
It really does.
You're taking something that has historically been viewed strictly through the lens of pathology, like essentially a biological error, and reframing it as this ultimate thermodynamically perfect engineering substrate.
And that reframing is exactly the mission of our deep dive today. Okay, let's unpack this. Because we are looking at a massive, highly technical, and frankly mind-bending 2026 manifesto by an independent researcher named Zachary David Enfield.
Yeah, the document is titled Prion and Amyloid Architectures, a Total Application Framework.
And we have a whole stack of documents here, including multiple addendums and supporting research papers that propose using the unique physical structure of prions to build literally everything.
We are talking about nanocomputers, nuclear batteries,
Self-healing aerospace composites, yeah.
and eventually self-replicating space infrastructure that could span an entire solar system.
It's huge. So I want to promise you, the listener, that we are going on a journey today, one that starts at the microscopic quantum scale, zooms out to the cellular level, and then goes all the way up to the Kardashev Type III civilizational scale.
But I mean, before we get to building Dyson swarms out of biological matter, we need to understand the fundamental building block.
Right. What exactly are we looking at here? Let's define our terms.
So the foundational physical structure we are analyzing today is called the cross-beta amyloid scaffold. Now, I want to set a calm analytical tone right out of the gate here,
Good idea.
because I know the word prion carries a lot of baggage. If you are listening to this and immediately thinking of, like, mad cow disease, I totally get it. But I urge you to keep an open mind and also to think critically.
Yeah, because we weren't talking about diseases today.
Exactly. We are looking at a specific physical mechanism, the way these proteins fold and assemble into shapes, and analyzing how that specific architecture might radically outperform synthetic engineering.
Okay, so the cross-beta architecture, what is that exactly?
It's essentially a structural motif. It's not specific to one single protein sequence. It's a shape, a very specific geometric configuration that many different proteins can adopt under the right thermodynamic conditions.
Right, so we are divorcing the geometry of the protein from the disease. We're literally just looking at the shape.
Yes.
And before we can even conceptually build a solar system spanning megastructure out of this stuff, we have to understand what makes this specific biological material so indestructible and so uniquely powerful.
Let's zoom all the way in.
Yeah, let's look at the indestructible nanoscaffold itself.
Yeah.
How is this cross-beta architecture actually put together at the molecular level?
Okay, to visualize this, we first need to understand how a normal protein behaves. Think of a standard protein like a long, flexible string of beads,
Okay, string of beads, got it.
where each bead is an amino acid. In a normal, healthy cellular environment, that string folds up into a very complex, tangled, three-dimensional shape. It looks like a crumpled-up ball of yarn.
Oh, right, because they have to fit together in a certain way.
Yeah, it folds that way because certain amino acids repel water, so they hide in the center, while others are attracted to water, so they form the outside. That complex 3D shape dictates what the protein does in your body.
It's like a highly specific tool, right, shaped exactly for one job, like an enzyme that breaks down sugar.
Precisely. But the cross-beta architecture is a radical departure from that crumpled ball. Imagine a microscopic fibril, like a tiny thread. In this misfolded state, the protein just abandons that complex 3D tangle entirely.
It just lets go of the shape.
Yeah, the string straightens out into what we call rigid beta strands. And these strands orient themselves perpendicular to the long axis of the growing thread. They stack on top of each other one by one.
Like a ladder.
Sort of, but flat. And they are bound together by a dense interlocking network of hydrogen bonds. This creates incredibly tightly packed sheets running parallel to the axis of the thread.
So if you're trying to picture this, imagine a stack of molecular paper plates just stacked endlessly on top of one another. Or maybe think of a zigzag folded piece of paper, like an accordion.
Oh, that's a great way to look at it.
And you just keep stacking more accordions on top of each other, and they interlock perfectly.
That accordion analogy is excellent. Because they interlock so perfectly, the mechanical performance of this stacked structure is absolutely staggering. When we look at polymeric amyloid fibers, specifically engineered ones, not the naturally occurring pathological ones, the experimental literature shows they reach a toughness of 160 megajoules per cubic meter.
Okay, 160 megajoules per cubic meter. That might just sound like a big, meaningless number to people, so let's put that into perspective.
Please do.
That toughness benchmark actually beats natural spider dragline silk. And for decades in materials science, spider silk has been the absolute holy grail. It's the gold standard for biological toughness.
That really is.
But here's the real kicker. This protein fiber operates at 1/8 the density of structural steel. So it is ridiculously light, insanely tough, and it's made out of the basic building blocks of life.
It completely alters the strength-to-weight ratio paradigms we usually rely on in aerospace and civil engineering. But mechanical toughness is really only half the story here.
Right, there's the chemical side.
Exactly. The chemical stability is what makes this material truly alien compared to traditional biology. Because of how densely packed those beta sheets are, those interlocking accordions you mentioned, the internal bonds are shielded from the outside environment.
Shielded how? Like a force field?
Physically shielded. Water molecules literally cannot penetrate the core of the fibril. Because of this shielding, these fibers survive boiling in concentrated sodium hydroxide. They survive pure formic acid.
Wait, I really want to emphasize that. Boiling acid. For a protein.
I know, it's wild.
If you put a normal piece of biological tissue or even a synthetic plastic into boiling sodium hydroxide, it dissolves into an unrecognizable soup. But this protein structure just sits there completely unbothered.
Yeah, and they even survive gamma-ray irradiation at doses that would completely shatter the atomic lattice of conventional silicon logic chips or degrade copper wires. That's just unbelievable. So how do material scientists actually control this? Because if it's this tough, it sounds really rigid. But sometimes, you need a material to be flexible.
Right. And this brings us to the underlying control mechanism, the real engineering breakthrough. It all comes down to what is called hydrogen bond density, or HBD.
HBD, okay.
The hydrogen bonds are essentially the molecular superglue holding those stacked plates together. By changing the specific amino acid sequence of the protein, just using standard genetic engineering techniques, researchers can precisely dictate how many hydrogen bonds form inside the core of the fibril.
Oh, so it's essentially a tuning dial. You tweak the genetics to dial the physical properties up or down.
A structural rheostat, if you will. Yeah. If you sequence the protein to maximize the hydrogen bond density, you get a material that is rigid, unyielding. It's a biological analog to structural steel or Kevlar.
But what if you dial it down?
If you turn that HBD dial down, intentionally creating a more disordered, looser core, the fibril becomes highly dynamic. It becomes flexible, and more importantly, it becomes fragile. Fragile. Wait, in traditional engineering, fragility is a flaw. Why would we want that?
Well, in the world of prions, fragility is the key to rapid exponential self-replication.
Oh, I see where you're going with this.
Yeah.
Because of the templating cascade mechanism? Let's really break this down for the listener, because understanding this cascade is the engine that drives the entire 2026 manifesto.
Absolutely.
If I have a liquid solution full of normal, unfolded monomer proteins just floating around harmlessly in a vat, and I drop one of these fragile, misfolded fibril seeds into the bath, what happens?
That single seed acts as a physical template. It possesses a highly favorable, lower energy geometric state.
Okay.
So when a normal protein bumps into the tip of that seed, the physical geometry of the seed forces the normal protein to unfold. It adopts the exact same misfolded shape, instantly snapping onto the end of the stack.
So it physically bullies the normal proteins into changing shape.
That's one way to look at it. And once that new protein snaps on, it becomes part of the template. Now it's capable of converting the next protein that bumps into it. Now, if the fiber is long and rigid, it only grows from its two ends. But if you dial down the hydrogen bond density so the fiber is fragile, the thermal motion of the liquid causes the growing fiber to snap in half.
Ah, and when it snaps, you suddenly have 4 growing ends instead of 2. And then those grow and snap, giving you 8 ends. then 16.
Exactly. It becomes an exponentially growing, self-assembling structure. The kinetic rate of assembly just skyrockets.
It's like having a giant swimming pool full of loose, floating Lego bricks. And you drop in one pre-assembled block of 4 Legos. Suddenly, that block starts magnetically pulling the loose bricks out of the water, snapping them into a perfect replica of itself. Over and over, until the entire pool is a solid skyscraper that can survive an acid bath.
And consider the manufacturing implications of that. The energy cost of that assembly process approaches zero.
Yeah.
To build a steel beam, you need a massive, high-temperature smelting factory burning coal or natural gas. To build an amyloid structural beam, you need a bioreactor at room temperature, a liquid protein feedstock synthesized by basic yeast or bacteria, and a single microscopic seed.
That's it.
That's it. The material fundamentally grows itself using the ambient thermal energy of the room.
Okay, I am totally on board with the efficiency of this. But I have to push back here, because as I was reading this manifesto, a massive practical concern kept glaring at me.
Let's hear it.
If this material is truly that indestructible, like immune to the natural enzymes that break down normal proteins, immune to boiling acid, immune to radiation, what happens if a structure grows out of control?
Containment.
Yeah. Or let's say we successfully build a self-assembling bridge out of this stuff. 50 years later, we want to tear it down to build a bigger one. How do you demolish a material that is immune to everything? Are we just creating unkillable biological trash that will persist in the planetary environment forever?
It is arguably the most vital question to ask when discussing self-replicating synthetic biology. You are essentially asking about the containment and life cycle management of an indestructible substance.
Right. It sounds terrifying.
Right, but the Enfield text addresses this directly, and it ties back to that tuning dial we talked about. The designer of the material completely controls the hydrogen bond density. You can engineer low HBD fibers that are explicitly designed to be vulnerable to environmental moisture or UV light, degrading naturally within days or weeks.
Okay, but what about the permanent structures? The high HBD stuff we use for buildings or spaceships. You don't want your spaceship melting in the rain.
For the permanent, ultra-tough materials, the framework specifies the mandatory integration of a structural kill switch. And this is a marvel of bioengineering. You don't demolish the bridge with dynamite or acid. You use molecular scissors.
Molecular scissors.
Yeah. Researchers can engineer specific RNA ribozymes or CRISPR-edited chaperone proteins that are tailor-made to recognize the exact, highly specific synthetic sequence of that one particular amyloid fold.
So you create a bespoke chemical key that only fits that specific lock.
Precisely. When deployed, perhaps sprayed over the structure or introduced into its fluid network, these biological agents bind to the structure and cleave specific vulnerable bonds that were intentionally engineered into the cross-beta lattice.
Wow.
The structure immediately disaggregates. It just unzips back into harmless base amino acids. The designer dictates the dissolution just as precisely and as effortlessly as the assembly.
Okay, so we have a material that is incredibly tough, compositionally tunable, immune to extreme environments, and self-assembling from a room temperature liquid bath, complete with a built-in self-destruct mechanism.
It's an incredible foundation.
It really establishes an incredible physical foundation. But, a strong brick is still just a brick. If we were going to build a technological civilization, we need electronics. We need power.
Absolutely.
What happens when we try to pass energy through this protein? Can this indestructible nanoscaffold actually do work? This takes us into the electronic and piezoelectric properties of the material, what the author calls the biological power cord.
This is where the framework moves from passive structural materials into active, functional nanoelectronics. The leap from inert to active. The foundational proof of concept for this actually goes all the way back to a 2003 experiment by material scientist Thomas Scheibel and his colleagues.
Oh, early 2000s.
Yeah. They took yeast prion fibers, again, non-mammalian, perfectly safe yeast proteins, and used them as microscopic templates for gold deposition.
Wait, let me make sure I'm visualizing this correctly. They took this microscopic protein thread, put it in a solution with gold particles, and the protein basically acted like a magnet, just pulling the gold out of the liquid and wrapping itself in it.
That is functionally what happened. The biological fibers self-assembled first, establishing the geometric line. Then, specific amino acids on the exterior of the fibril chemically reduce the gold ions in the solution, causing solid gold nanoparticles to nucleate directly onto the protein surface.
That's brilliant.
They created a highly conductive, continuous metallic nanowire, and they did it without needing any toxic silicon substrates, high-heat vapor deposition, or multi-million-dollar clean room lithography. The wire grew itself from the bottom up.
That alone is amazing for manufacturing. But as I read further into the stack of sources, the text goes even further than just using the protein as a coat rack for metal. Fast forward to 2021, a breakthrough study by Ships and colleagues show that amyloid crystals can conduct electrons intrinsically,
Yes.
without any gold or metal coating whatsoever, a pure protein that conducts electricity. The paper said they do this through a process called tyrosine hopping. What on earth is tyrosine hopping?
To understand this, we have to look at the specific atomic structure of the amino acid tyrosine. Tyrosine features what chemists call an aromatic ring, a hexagonal ring of carbon atoms. Now, in this ring, the electrons aren't locked tightly to individual atoms. They form a delocalized cloud that hovers above and below the ring.
Like a microscopic halo of negative charge.
Yes. Now, imagine what happens when these tyrosine residues are packed incredibly tightly together in the dense core of the amyloid fibril we described earlier. Because the cross-beta architecture stacks everything so perfectly, these tyrosine rings end up stacked directly on top of each other, just nanometers apart.
Okay, I'm picturing the stack again.
When they stack, those electron halos overlap. This is a quantum mechanical phenomenon known as pipey stacking.
So instead of a bunch of isolated halos, the overlap creates a continuous tube of electron clouds.
Precisely. It creates a continuous orbital pathway. When you introduce an electron at one end of the fiber, it doesn't have to push its way through a chaotic biological soup. It simply hops along this continuous pi-p stacked pathway over micrometer distances. It transforms an insulating biological material into an intrinsic, organic semiconductor.
That is wild. It's essentially a biological copper wire. And it's not just electrons either. I saw a 2024 study by Navarro mentioned in the manifesto showing these fibers can conduct protons too.
They can.
In fact, their proton conductivity surpasses the performance of synthetic petroleum-based polymers that we currently use in hydrogen fuel cell membranes.
What's fascinating here is how multifunctional it is.
Yeah, so we have electrons, we have protons.
Yeah.
But here's the property that really stopped me in my tracks. Piezoelectricity.
Yes.
I've heard the term, usually in relation to quartz watches or those little clickers on gas barbecues, but explain how it works in a protein.
Piezoelectricity, at its most fundamental level, is the generation of an electric charge when a material is mechanically deformed. You squeeze it, bend it, or subject it to physical stress, and it responds by generating a voltage.
Right.
The reverse is also true. If you apply a voltage, the material physically changes shape. In materials like quartz, this happens because the crystal lattice is highly ordered but asymmetric. When you compress it, you physically push the positively and negatively charged ions out of their resting balance, creating an electrical dipole moment of voltage.
And these misfolded amyloid fibers do that.
They do, and with astonishing efficiency. Because of the non-centrosymmetric crystalline structure, meaning it lacks a center of symmetry, of those heavily hydrogen-bonded beta sheets, these fibers have a highly permanent dipole. When you flex them, hit them with sound waves, or apply any mechanical stress, they generate an electric charge. And what is truly revolutionary is that they're piezoelectric constants. The measure of how efficiently they convert mechanical energy into electricity match, or even approach those of classical industrial ceramics, like lead zirconate titanate, which are toxic and brittle.
Let's just pause and appreciate the absurdity of this.
A lot to take in.
We're talking about a microscopic thread, maybe 10 nanometers wide. It is simultaneously a structural support beam, tougher than steel, an electrical semiconductor moving electrons, a proton membrane for fuel cells, and a power generator that creates electricity just by being wiggled. It is an all-in-one infrastructural metamaterial.
And returning to the concept of the tuning dial, you can optimize all of those electrical and mechanical properties by simply mixing and matching the biological building blocks.
How so?
Well, a 2022 study by Zhang demonstrated a concept called co-assembly enhancement. Instead of using one type of protein, they mixed two slightly different peptide sequences together in the same liquid bath.
Like blending two different types of Lego bricks.
Yes, and as the fibril self-assembled, it incorporated both sequences into an alternating, highly ordered composite crystal. This composite material increased its piezoelectric output by 38%, and its overall voltage by 300% compared to the single protein version.
Wow.
The macroscopic electronic properties of the material are infinitely tunable just by changing the microscopic protein recipe in the vat.
I want to ground all this high-level physics with a real-world example from the text, because the medical applications Enfield proposes are just wild. Let's look at the wireless cell therapy example.
Yeah, it's a great one.
This is based on a 2024 paper by a researcher named Dolai. They took these piezoelectric amyloid fibrils and injected them directly into a malignant tumor in a living subject. Just a liquid injection of these tiny, self-assembled fibers. Then they stepped back and hit the tumor from the outside with standard, non-invasive ultrasound waves. Just regular sound waves.
And we know sound waves penetrate soft tissue harmlessly.
Exactly. But when they hit the dense amyloid fibers embedded in the tumor, the sound vibrations cause the fibers to flex rapidly.
And because we established that these fibers are highly piezoelectric, that rapid physical flexing generates an electrical current. They are converting acoustic energy into electrical energy right there in the tumor microenvironment, generating up to 1 volt of electricity.
And what does 1 volt of electricity do inside a tumor? It drives intense electrochemical reactions with the surrounding water and oxygen, creating what are called reactive oxygen species, or ROS.
Which are fundamentally highly volatile molecules that cause extreme oxidative stress to cells.
Right, they act like molecular bleach. They are highly toxic to the cancer cells. The ROS literally shreds the cancer from the inside out.
It's incredible.
So, to summarize, you are wirelessly generating a targeted, toxic electrical stress to kill a tumor, using harmless sound waves and self-assembling proteins. No implanted batteries, no wires breaking the skin, no toxic chemotherapy flooding the whole body. And when the job is done, the fibers eventually just degrade into harmless amino acids that the body absorbs as food.
It functions as a totally self-contained, externally powered therapeutic transducer. It represents a total paradigm shift in nanomedicine.
Okay, here's where it gets really interesting for me and where I found myself getting stuck.
What's the sticking point?
This material is basically a biological power cord that not only grows itself, but harvests energy from the ambient vibrations of the room or sound waves or just physical movement.
Yeah.
But I keep coming back to a spatial problem.
The geometry.
Yeah. We've talked about dropping a seed into a vat and letting it exponentially grow into a solid block.
Yeah.
But if I want to build a computer circuit board, not just a tangled random ball of wire, how do I tell it where to grow?
Yeah.
If the templating cascade just shoots off in every direction wherever there are free proteins, how do I force it to grow a perfectly straight wire, turn a precise 90-degree corner, and connect to a specific node? Without spatial control, you just have a vat of very strong conductive sludge.
Your intuition is spot on. That exact problem, the lack of spatial geometric control over the exponential templating cascade, was the major bottleneck for amyloid engineering for over 2 decades.
Really?
Oh, yeah. Researchers could grow bulk materials, they could grow fibers, but they couldn't rate intricate architectures. They couldn't draw a circuit. And that limitation leads directly into the framework's next major technological leap, which involves combining prion self-assembly with the physics of light.
This was the most sci-fi part of the first half of the manifesto. Sculpting with light, prion optogenetic lithography. Break this down for us. What is optogenetics?
Optogenetics is a field of biology that involves the genetic encoding of light-responsive protein domains. In nature, certain organisms, like plants or specific algae, have proteins that react to sunlight so the organism knows which way to grow.
Sure. Scientists isolated these specific protein segments, known by acronyms like Cry2 or LOV2, which literally change their three-dimensional physical shape when they absorb a very specific wavelength of light, like blue light or red light.
They act as molecular light switches. You hit them with a photon, they pop open.
That is an incredibly accurate way to visualize it. So the synthesis Enfield proposes here, prion optogenetic lithography, involves fusing one of these light-responsive domains directly to the end of a prion-forming sequence.
So you take this self-assembling Lego brick and you genetically staple a light switch to the top of it. What does that actually do?
In the dark, the light-responsive domain acts like a physical lock. It sterically blocks the prion sequence.
Hold on, let me clarify that term. Sterically blocks, you mean it's literally just acting as a physical lid sitting on top of the protein, physically preventing other molecules from touching the sticky part? Yes, steric hindrance just means 2 physical objects cannot occupy the same space. The light domain folds over the prion domain like a lid. Because the lid is closed, the prion cannot misfold, and it cannot interact with other proteins.
Okay, so they just float there.
Exactly.
Yeah.
So you can have a giant vat of this liquid protein solution, and in the dark, it just sits there. It is completely harmless, dormant, and liquid. But the moment you shine that specific wavelength of blue light into the vat, the photon hits the lid. The energy from the light causes the lid to change shape and swing open.
And suddenly this sticky prion sequence is exposed to the environment.
Precisely. Once exposed, it adopts its misfolded state, and it immediately begins the self-assembling, templating cascade we discussed earlier. It starts grabbing its neighbors. But, and this is the crucial part, it only happens exactly in the area illuminated by the laser.
This completely bypasses the need for traditional physical molds, casts, or the mechanical nozzles of modern 3D printers.
It replaces all of that.
If you are listening, just picture this. You have a giant glass vat of crystal clear liquid protein. You take a highly complex holographic light projection, like a 3D laser image of microscopic gear or a vascular network, and you shine that 3D hologram directly into the center of the liquid. In a matter of milliseconds, a solid, highly complex 3D structure will instantly begin growing out of the liquid, matching the exact geometry of the light. You are literally pulling solid objects out of thin air using photons.
And the spatial resolution of that object is limited only by the diffraction limit of the light you're using to draw it. If you use extreme ultraviolet light, you can draw structures atom by atom. The manifesto highlights a 2025 Nature Communications paper detailing what is called the PHOBIT system.
PHOBIT?
Yes. This system allows for highly reversible modular light-controlled protein interactions. You can use blue light to trigger the assembly, and in some engineered variants, you can switch the light to a different wavelength to snap the lid shut again, halting the propagation at the exact microscopic boundaries you desire.
The extrapolation of this technology is staggering. The manifesto dives into a few applications. Let's look at tissue engineering first.
Right.
If someone is brought into a hospital with a severe traumatic wound, say a massive gouge in their muscle tissue, you could inject this dormant protein liquid directly into the cavity of the injury. Then, using targeted external light, perhaps piped in through a tiny fiber optic cable or targeted external lasers, the surgeon writes a regenerative scaffold perfectly shaped to the exact irregular geometry of that specific wound.
And because we know the material can be tuned via hydrogen bond density, that light-written scaffold isn't just a dead plug. It provides the exact structural support the surrounding cells need to anchor onto. Furthermore, it can be engineered to release chemical signaling gradients that tell the body to grow new blood vessels into the scaffold.
And then just melts away.
Once the natural tissue has healed over it, the low HBD scaffold safely dissolves.
Another application the text dwells on is food technology. They call it protein lattice printing. We're talking about the holy grail of lab-grown meat. Right now, lab-grown meat often ends up as a kind of mush because it lacks the complex 3D structure of real muscle and fat.
Yeah, texture has been the biggest hurdle.
But with this, you can create the exact microscopic texture of muscle fibers, the literal, physical snap and chew of a steak or a shrimp tail, by guiding the amyloid growth with light in a bioreactor. It requires zero animal agriculture, zero slaughterhouses, and uses a tiny fraction of the water and energy. You can program the exact nutritional profile and the mouthfeel just by changing the holographic light pattern and the protein mix in the vat.
It completely decouples the geometry of our food from the biology of the animal. You are writing the texture with photons. It solves the scaling problem of cellular agriculture overnight.
Okay, I have to interject here again because while this sounds like literal magic, my brain is snagging on the physics of the cascade again.
Sure, lay it on me.
I'm imagining this vat of protein. I shine my incredibly sharp, high-resolution laser into it to draw a wire. The light opens the lids of the proteins in that specific beam, and they start misfolding and attaching to each other. But wait, if one activated protein converts its neighbors, and they convert their neighbors in an exponential cascade, wouldn't the growth immediately bleed past the illuminated area?
Ah, I see what you're asking.
As soon as the first solid seed forms inside the light beam, what stops that seed from just poking out into the dark liquid, grabbing the dark proteins, forcing them open, and solidifying the entire vat anyway? How does the light pen actually maintain its high resolution without the fire spreading?
It is a very astute objection, and to be fair, the author acknowledges this is the primary design challenge of the entire platform. The cascade naturally wants to amplify and spread.
Right.
The solution Enfield outlines involves a highly complex, multi-pronged thermodynamic control strategy. First, you strictly control the monomer concentration in the vat. You keep the amount of loose protein just below the threshold where spontaneous rapid growth can sustain itself.
Like keeping the amount of oxygen in a room just low enough that a spark won't cause an explosion.
Exactly. Second, you utilize competing capping agents in the dark zones of the vat. These are specially engineered molecules that naturally bind to the growing ends of fibrils and permanently stop them from grabbing anything else.
Ah, so you have molecular firefighters constantly swimming around in the dark areas, actively fighting and capping any growth that tries to escape the light.
Correct. But the most important and elegant factor is engineering the kinetic barrier to nucleation. The system is thermodynamically designed so that the self-assembly cascade strictly requires continuous, active photonic energy to overcome the constant barrage of local capping agents and propagate long distances.
Okay, so it needs constant power.
Exactly. The moment the fibril tip grows a millimeter out of the laser light and into the dark, the local dark state dynamics overpower it. The capping agents swarm it, the energy gradient drops, and growth halts instantaneously. The light doesn't just start the fire, it has to constantly actively feed it for it to spread.
Okay, that makes perfect sense. Let's take a breath and review where we are, because the scale of this is building rapidly.
We've covered a lot.
We now have an indestructible, highly tunable, electrically conductive material. It can generate its own power from ambient sound or vibrations, and we can 3D print it into any microscopic or macroscopic geometric shape instantly using holograms of light in a room-temperature liquid bath. That alone is a world-changing revolution in material science.
But it's just the beginning.
Right. The manifesto argues that is just the chassis. The next logical step is to use this exact material to build a brain, or, more accurately, a thermodynamically perfect computer.
This brings us to a massively complex part of the text, the 8-layer thermodynamic molecular computer. This is where the framework firmly transitions from advanced materials science into the frontiers of quantum information theory and computational physics.
To understand why we would even want to build a computer out of protein and DNA, we have to look at the physical wall that traditional silicon computing is hitting right now. If you look at modern data centers, the ones running artificial intelligence, global finance, cloud storage, they're consuming the energy output of entire power plants.
Huge amounts of energy.
And a massive percentage of that energy isn't even used for calculation, it's used for cooling.
Right, and that heat isn't just friction from electricity moving through wires. It is rooted in a fundamental law of physics known as Landauer's principle.
Let's really dive into this because this concept blew my mind. What is the Landauer limit?
In 1961, a physicist named Rolf Landauer proved that in any classical computational system, like the silicon chips in your phone or a supercomputer computation, is fundamentally an act of destruction.
An active distraction.
Yes. Let's look at a standard logic gate, like an AND gate. An AND gate takes two inputs, say a 1 and a 1, and produces a single output, a 1.
So you start with 2 bits of information and you end up with 1 bit.
Exactly. You have irreversibly lost a bit of information. The system has fewer possible states than it started with. Landauer proved, using the laws of thermodynamics, that erasing a bit of information fundamentally decreases the entropy of the computational system, and therefore it must expel a minimum amount of heat into the surrounding environment. It is a thermodynamic law. You cannot erase information for free.
That is profound. The heat coming off my laptop right now isn't just electrical resistance. It is the physical thermodynamic cost of deleting data. It is the exhaust of erased information.
That's a great way to put it. And as we pack more and more transistors onto silicon chips, doing billions of calculations per second, that unavoidable heat generation becomes a hard physical barrier. The chips will literally melt themselves.
But the biological architecture Enfield proposes doesn't work this way.
Not at all. Let's walk through the key layers of this 8-layer unified computational architecture.
We've already established layers 1 and 2 of this biological computer. Those are the electron transport pathways and the piezoelectric inputs we talked about. That's the power supply and the basic physical wiring.
Then we move to layer 3, which utilizes RNA as the real-time regulatory execution layer. In a biological cell, RNA operates almost like the working memory and the logic gates. It uses structures called riboswitches and RNA logic circuits to sense the environment and make rapid, context-dependent decisions.
So RNA is the middle manager, making sure everything flows correctly. Layer 4 is where our misfolded prion fibers come back into the picture. They act as the physical logic interconnects. Instead of binary electrical switches, which are just voltage on or voltage off, the prions use their conformational cascades to act as non-binary logic gates.
Meaning they physically route the information based on their shifting three-dimensional shapes. The geometry of the protein is the logic gate.
And at the very foundation of the memory architecture, layer 6, we have DNA acting as quaternary storage. And this is where the density becomes almost unfathomable. Instead of silicon binary, storing ones and zeros, DNA has 4 base pairs: adenine, cytosine, thymine, and guanine, A, C, T, G. This allows DNA to encode 2 bits of information per individual base pair.
The information density achievable in 3D space with DNA is something silicon simply cannot physically match. You could store the entire internet in a volume the size of a shoebox. But returning to Landauer's principle, the real paradigm shift here isn't just the storage density, it's the computational efficiency.
How does a computer built out of DNA and protein beat the heat limit?
Because the prion DNA architecture doesn't erase bits, it operates on the principles of reversible computing. It uses those conformational cascades to copy and propagate states without destroying the previous state.
So it's non-destructive.
Exactly. When a prion fiber interacts with a DNA storage node to read data, it physically changes its shape to match the information, but it doesn't destroy the original state of the DNA to do so. Because information is conserved in the geometry of the molecules rather than destroyed and overwritten, it generates almost zero heat per calculation. It approaches the theoretical thermodynamic floor of perfect efficiency.
And this brings us to what Enfield dramatically calls the total descent destruction moment in the manifesto. Because critics of biological computing have pointed out what seems like a fatal flaw in this whole setup.
Yes, the clock speed problem.
To clock this DNA computer, to make it run fast enough to be useful, rather than operating at the slow speed of a crawling cell, the framework proposes using terahertz radiation to rapidly unzip and rezip the DNA strands.
Terahertz radiation sits between microwaves and infrared light on the electromagnetic spectrum. It vibrates very quickly.
Right. But, as critics rightly point out, terahertz radiation is heavily absorbed by water. And biology, by definition, requires a wet environment. So if you blast terahertz radiation into a wet DNA computer to speed it up, the water absorbs the radiation, creating intense friction. It creates heat. And supposedly, that heat would literally boil the water and denature the delicate molecular computation, destroying the computer.
It is the most technically grounded, rigorous objection to the framework. And Enfield's rebuttal relies on a paradigm-shifting paper published in Nature in 2025 by researchers Song and Key at Caltech. The rebuttal completely flips the problem on its head.
This part is amazing.
The answer is simply this. Heat is not the enemy of this architecture. Heat is the battery.
Okay, I need you to walk me through this slowly. Every time my laptop gets hot, the fans kick on roaring because heat destroys the circuitry. How can heat possibly be the battery for a computer?
It requires abandoning classical mechanics and embracing the core principle of thermodynamic computing. The Caltech researchers demonstrated that a thermal cycle, literally just raising and lowering the temperature of the fluid environment, actually recharges enzyme-free DNA logic circuits.
Recharges them.
Yes. In a resting state, the DNA logic gate reaches a chemical equilibrium. It's done its calculation, and it sits there, inert. The heat pulse from the terahertz radiation provides a burst of kinetic energy. It violently restores the DNA from its resting equilibrium back into an out-of-equilibrium state, highly energized and ready to compute the next logic step.
So the heat doesn't melt the wire. The heat cocks the hammer back on the molecular gun so it can fire again.
That is a very apt analogy. The framework doesn't try to isolate the computer from the ambient thermal bath of the water with massive cooling systems. It actively embraces the environment, harvesting that chaotic thermal energy to power the physical movement required for the next calculation.
And there was another massive study supporting this thermodynamic approach, right? The LNU Munich 2025 paper.
Yes, the Brownian DNA computing concept. Brownian motion is the random, chaotic jittering of water molecules as they constantly bounce into each other at room temperature. The LMU researchers showed that this random, chaotic thermal motion can actually be harvested as the computational engine driving molecular balances on a DNA origami platform.
So if the DNA computer is a sailboat, we aren't trying to attach a massive, heavy, power-hungry outboard motor to push it through the water. We are literally designing the sails, the protein shapes, to perfectly capture the chaotic thermal wind of the water itself to move the computation forward.
The ambient noise of the universe provides the propulsion.
It's beautiful in theory, but I still have a hard time wrapping my head around the reliability. If my silicon computer flips one single bit by accident, the whole program crashes. Isn't a computer built out of wobbling, fluctuating, wet proteins, constantly being bashed around by random heat, inherently prone to massive catastrophic errors compared to a rigid, frozen piece of silicon?
In a classical rigid framework, yes, the noise would destroy the signal. But this biological system uses a concept called thermodynamically favored equilibrium. The system is specifically geometrically engineered so that the correct logical output of a calculation represents the lowest possible free energy state for those specific molecules.
What does that mean in physical terms? Like, practically?
Imagine dropping a marble onto a rugged landscape full of hills and valleys. The marble naturally wants to roll down into the deepest valley. In this computer, the deepest valley represents the mathematically correct answer of the calculation. The thermal fluctuations, the random wobbling and shaking from the heat act like tiny earthquakes on that landscape.
So if the marble gets temporarily stuck in a shallow valley, a false state or an error, the random shaking of the heat actually knocks it loose.
Exactly. The thermal noise shakes the system out of temporary false states and drives it relentlessly downward toward the lowest energy state, which is the correct answer. The ambient heat doesn't cause errors. It is the mechanism that naturally and continuously corrects errors without requiring the massive, energy-intensive error-checking algorithms that classical computing demands.
That is profound. The noise is the error correction. The system's efficiency doesn't just rival silicon. It bypasses the fundamental physical limits of silicon entirely, which moves us perfectly into Section 5 of the manifesto, pushing limits. Because if you have a computer that operates near perfect thermodynamic efficiency, harvesting the thermal background of the universe, the next logical step for a technological civilization is moving into the realm of quantum operations at room temperature. Let's talk about photonic quantum computing.
The framework takes all the materials we've discussed and scales them into quantum physics. It establishes that the metallized prion fiber lattices, those self-assembling gold-coated nanowires we discussed earlier, are intrinsically helical. Because they are built from biological proteins, they naturally have a physical twist, a chirality to their structure.
Right, like a microscopic spiral staircase.
And that chiral geometry isn't just aesthetic, it has profound optical properties. It allows these nanowires to act as highly specialized waveguides for light. They can selectively route photons based on their polarization, specifically distinguishing between left circular or right circular polarized photons.
Okay, why is that important?
In the world of quantum computing, photon polarization is routinely used to encode quantum bits, or qubits. The ability to passively, perfectly route these photons based on their spin polarization is exactly the physical hardware required to build what physicists call a KLM linear optical quantum computer.
So the protein fiber is naturally shaped by billions of years of evolution to be a perfect quantum logic gate for light. But as wild as biological quantum computing is, we need to talk about the nuclear convergence.
This is a big one.
Enfield refers to this in the text as the coalescent transducer. This is the point in the reading where my jaw actually dropped. This is where the framework proposes fusing a uranium-binding protein sequence directly into our self-assembling amyloid scaffold.
Yes. To understand why this is such a revolutionary leap in energy generation, we have to look at the severe limitations of traditional nuclear batteries, which are known as beta voltaics. In a traditional setup, used in things like deep space probes, you have a solid chunk of radioactive material sitting next to a semiconductor panel. As the radioactive isotope decays over decades, it shoots out high-energy electrons.
And the semiconductor catches the electrons to make power.
In theory. But in reality, many of those high-energy electrons collide with other radioactive atoms inside the chunk of fuel before they ever reach the edge to hit the semiconductor. This is a massive inefficiency known as self-absorption. The fuel essentially blocks its own energy output.
You're losing the energy inside the battery itself.
Exactly. But the coalescent transducer, which was conceptually validated in a 2024 Nature paper, solves this problem geometrically. You don't build a chunk of fuel and put it next to a wire. You engineer the amyloid fiber itself to contain specific molecular claws chillers that actively bind uranyl ions.
Molecular claws.
The protein literally pulls individual uranium atoms out of a liquid solution and locks them directly into the crystal structure of the wire at angstrom scale proximity. You erase the gap entirely. The radioactive decay event happens inside the conductive transducer.
There is zero self-absorption because every single atom of fuel is already embedded perfectly inside the wiring, and because we already know the amyloid fiber is an absolute multi-tool, it doesn't just catch the electron. It harvests that single nuclear decay event in 3 different ways simultaneously, right?
Yes, it is a trimodal energy harvester. First, beta voltaic harvesting. It captures the high-energy electrons ejected by the decay directly into that highly conductive tyrosine piping network we discussed. Second, piezoelectric harvesting. When the heavy uranium atom decays, it violently recoils, sending a physical shock wave vibrating through the crystal lattice.
And because the lattice is piezoelectric, it turns that physical recoil vibration directly into a spike of electricity.
Precisely. And third, it harvests the thermal gradients, the localized heat created by the decay process using thermoelectric properties. It wrings every possible drop of energy out of a single decaying atom.
I think it's important to note here for the listener that blending biology and quantum mechanics isn't just science fiction. Biology already plays with quantum mechanics every single day. Photosynthesis in plants uses quantum coherence at room temperature in something called the FMO complex.
Oh, absolutely.
The plant literally puts the captured light energy into a quantum superposition to test every possible route to the reaction center simultaneously, transferring the energy with near-perfect 100% efficiency.
Yes, the FMO complex proves that the warm, wet, messy environment of biology can sustain delicate quantum states. The framework argues that the amyloid's periodic, highly ordered hydrogen bond lattice acts as a phonon bath. It absorbs the chaotic, destructive vibrations of the environment to protect the delicate quantum electron transport in the exact same way a plant protects a photon. It proves that a sufficiently advanced civilization can handle quantum effects outside of a multi-million-dollar absolute zero cryogenic laboratory.
But okay, I have to stop you there. I have to play the skeptic, the advocate for the terrified listener right now.
Go ahead.
Putting radioactive uranium inside a self-assembling, exponentially self-replicating biological material that runs on quantum physics sounds exactly like the setup for a planetary extinction-level sci-fi horror movie. Are we talking about growing a literal nuclear reactor in a vat of pond scum? Because if that templating cascade gets out, we have radioactive zombies.
It is a completely visceral, understandable reaction, but we must clarify the terminology explicitly based on the physics outlined in the text. This is not a reactor.
Okay, please define the difference for my own sanity.
A nuclear reactor is actively designed to sustain, control, and amplify a fission chain reaction. You are forcing atoms to split, which shoot out neutrons that hit other atoms, causing them to split, releasing massive amounts of immediate energy and lethal radiation. If you lose control of a reactor, you get a meltdown. This biological framework does absolutely none of that. It is a solid-state nuclear battery.
So it's not splitting atoms.
No. It is passively capturing the natural, spontaneous, incredibly slow alpha and beta decay of a radioisotope that happens over thousands of years. It cannot melt down because it is physically incapable of sustaining a chain reaction. The atoms are too diffuse within the lattice. Now, the manufacturing process obviously requires incredibly strict biosafety and radiation containment protocols, but you are not growing a chain-reacting bomb. You are growing an ultra-efficient multimodal battery that can provide steady, reliable power for millennia.
Okay, thank you for clarifying that, because it is a vital distinction for the viability of this whole framework. So let's zoom out to the macro scale. We now have a biological material that computes at the thermodynamic Landauer limit using ambient heat, perfectly handles quantum photon routing, and acts as an ultra-efficient, room-temperature nuclear battery. What happens when an entire civilization standardizes this exact material for absolutely everything? This brings us to Section 6 of Enfield's Manifesto, the biological Type III node and civilizational infrastructure.
This section forces us to fundamentally redefine the Kardashev scale, which is the standard metric astrophysicists use to categorize advanced civilizations. Traditionally, the Kardashev scale judges the advancement of a civilization purely by its total energy output and its massive physical footprint.
Right, like Type 1, Type 2.
Exactly. A Type I civilization harnesses the total energy of its home planet. A Type II builds a massive steel Dyson sphere to enclose and harness its home star. A Type III colonizes and harnesses an entire galaxy. But this framework argues that focusing on the massive aggregate macro scale is a philosophical mistake. The focus should be on the node.
The node being the fundamental smallest unit of the civilization.
Correct, the biological node. Imagine an individual organism, perhaps a post-human or an engineered biological entity, whose very cellular architecture is the civilizational infrastructure.
Wow.
The organism's body inherently contains the DNA thermodynamic computer for processing, the piezoelectric energy harvesters in its muscular movements, the quantum waveguides in its nervous system, the viral nanite delivery systems in its bloodstream.
The text introduces the concept of holographic information geometry here. And this is a beautiful, if difficult concept. Just like every broken shard of a hologram still contains the entire 3D image encoded within it, every tiny microscopic tip of a cross-beta fibril in this node contains the exact geometric instructions needed to build the entire civilizational material stack.
It relies on the legendary physicist John Archibald Wheeler's concept of it from bit.
The idea that the physical universe is fundamentally made of information.
Exactly. In this biological framework, it from bit is made physically real. The information is the geometry, and the geometry is the material.
And when you apply that holographic node concept to stellar macroengineering, the paradigm completely shifts. Let's look at building a Dyson swarm to capture a star's energy. In a traditional steel and silicon paradigm, you would have to mine entire planets down to the mantle, smelt the ore using unimaginable amounts of energy, manufacture billions of rigid solar panels, and launch them into space using chemical rockets. It's a massive energy deficit just to build the thing.
But with the biological node,
Yeah, how does that work?
you send a highly compact, microscopic seed of engineered cyanobacteria to a lifeless, carbonaceous asteroid orbiting a star. That's it, one payload. The bacteria land. They begin to photosynthesize using the intense starlight. They literally eat the asteroid's carbon and trace minerals. And using the templating cascade, they biologically grow a continent-sized, gossamer-thin, piezoelectric, and photovoltaic amyloid membrane. The swarm builds itself exponentially from local floating materials.
It's just a plant growing in the sunlight, but the plant is a solar sail. And once that swarm surrounds the star, it doesn't just collect power to run lights. The text talks about the Gertzenstein mechanism.
Yes, the communication aspect.
Because the swarm is a vast electrically conductive network wrapping around a massive gravity well, it can generate a coherent star-sized electromagnetic field. And according to physics established back in the 1960s by Gertzenstein, a strong EM field in the presence of a static magnetic field can convert electromagnetic waves directly into gravitational waves,
Allowing the civilization to communicate across vast interstellar distances using gravitational waves, which pass seamlessly through planets, stars, and thick dust clouds without any signal degradation or interference.
And they can even use the swarm as a stellar tokamak by using the swarm's acoustic resonance, literally playing the star like a massive bell using concentrated sound waves and projecting massive magnetic fields inward. The civilization can squeeze the star. They can manage its internal plasma fusion rate, throttling it up to burn hotter or down to conserve fuel, effectively extending the lifespan of their sun by billions of years.
In this paradigm, the distinction between machine and organism is entirely erased. The civilization doesn't build infrastructure. The civilization grows itself from the ambient proteins and energy of the environment.
But I have one final massive question about this, and it brings us back to the horror movie scenario.
Okay, let's hear it.
If this galactic seed can just be shot at an asteroid, where it aggressively eats the rock and grows into a continent-sized Dyson swarm using the power of a star, what happens if that seed accidentally or intentionally lands on a planet that already has life? Like Earth. How do you prevent this incredibly efficient, perfectly optimized, self-replicating galactic biology from just outcompeting local life and consuming an entire biosphere like a gray goo nightmare?
The author explicitly addresses this in the final chapter, outlining what they call the ethical architecture of galactic seeding. A civilization capable of mastering this level of thermodynamic efficiency must engineer the biology to be geographically and chemically self-limiting. The seeds must be fundamentally designed so that they only activate in the presence of specific, rare trace substrates found solely on dead asteroids or in hard vacuum. They must be programmed to instantly denature when exposed to the complex, wet biochemistry of a living world. Furthermore, they must be equipped with remote deployable CRISPR kill switches, allowing the home civilization to dissolve the swarm via a broadcast signal if it mutates or crosses a planetary boundary.
So the technology requires perfect ethics to survive itself.
The text argues that managing this containment is the ultimate test of civilizational maturity. You cannot wield a Type III biological infrastructure with a Type I ethical framework. The civilization would destroy itself long before it reached the stars.
That is a chilling but deeply necessary perspective. Which brings us to our conclusion for this deep dive. Before we wrap up, I want to briefly touch on the recurring theme of prion safety one last time, just to ensure we leave you, the listener, with the correct grounded context. We talked a lot about biology eating asteroids and killing cancer, but it is absolutely vital to remember that all the engineered applications discussed in this manifesto use non-infectious yeast prions, like SUP35, an entirely synthetic, lab-created protein sequences.
Yes, the framework is borrowing the mechanism of self-assembly, the templating cascade. It is explicitly not importing the pathology of mammalian neurodegenerative diseases.
It is the difference between studying how a virus replicates so you can build a targeted, helpful gene therapy delivery vehicle versus deliberately engineering a lethal pathogen. The mechanics are similar, the intent and the physical components are entirely separated. We are using the biological motor, not the biological poison. When you step back and look at the awe-inspiring scope of the material Enfield has synthesized here, it's almost too much to hold in your head at once. We started with a single misfolded protein, a tiny geometric anomaly, smaller than a virus. We watched it become a 10-nanometer conductive wire tougher than steel, then a thermodynamic DNA computer running on ambient heat, then a coalescent nuclear battery, and finally a self-replicating biological Dyson swarm capable of squeezing a star and communicating through the fabric of gravity itself.
It forces a complete reassessment of what advanced technology is supposed to look like. We have been culturally conditioned to look for the shiny, the metallic, the rigidly constructed, the loud. This framework suggests that the ultimate manifestation of technology is soft, wet, self-healing, entirely silent, and grown from the bottom up.
And that leads me to a final, lingering idea that this text provoked for me. It's something I want you to mull over after you finish listening. If a civilization truly masters this biology, if they create a galactic infrastructure that runs on ambient heat, generates absolute zero waste, uses gravitational waves to communicate, and perfectly mimics the thermodynamic background of the universe to achieve land-hour efficiency, would we even be able to see them through our telescopes? We keep pointing our massive radio dishes at the sky, looking for the harsh, glowing signatures of giant metal machines, radio chatter, and wasted heat. But maybe the ultimate technological civilization just looks like perfectly quiet, highly efficient dark matter.
It's a profound thought. If technology approaches perfect thermodynamic efficiency, it becomes indistinguishable from nature itself.
The ultimate camouflage. The next time you see a spider web catching the light or a piece of moss quietly growing on a rock, extracting energy with perfect efficiency, take a closer look at the biology around you. You might just be looking at the blueprints for the stars. Thank you for joining us on this deep dive into the source material. Stay curious.